Welcome to Nerk's Coffee Talk. This is the beginning of a series of talks that will cover a wide variety of topics related to power. Our goal is to inform the viewer in a straight-to-the-point manner to make the best use of their time. Today's talk will be covering symmetrical components. This is today's agenda. We will briefly cover the history of symmetrical components, the transforms, and the meaning of each component. In a later talk, we will go over using symmetrical components to analyze faults. Charles Fortescue's paper on symmetrical components in 1918 was groundbreaking in the electrical industry. The orthogonal vectors he chose to decompose phase vectors into had meaning with relation to rotating machines and ground, and also greatly simplified the analysis of unbalanced networks. Symmetrical components are still extremely relevant over 100 years later. Here are the core concepts of sequence components. First, each set of three phasors has one and only one representation in the sequence space. The sequence domain is a decomposition of the phase domain. Second, the components were chosen because they have meaning. It is important to understand their meaning. Lastly, sequence components can be used to simplify analysis in much the same way using Fourier transformers simplified the analysis circuits. The one-to-one transfer to another domain allows for simpler methods to be used. Here is how you transfer from the phase to the sequence domain. All of this is just simply matrix multiplication, and while it is good to be able to do it correctly, don't get hung up on the math. It is much more important to understand the meaning of each sequence component. Take note that the alpha constant is a 120-degree rotation. The square is a 240-degree rotation. This allows for B and C phases to be represented by rotations of each sequence component's Hay phase. Here is a description of the positive sequence component. It consists of three phasors of equal magnitude that rotate counterclockwise and are the predominant component on the grid during normal operations. The phase rotation convention, ABC or CBA, is arbitrary, but its convention must be followed by generation and loads. Negative sequence has three phasors of equal magnitude and are separated by 120 degrees, just like positive sequence. The only difference between positive and negative sequence is the phase rotation. The phasors still rotate counterclockwise, but the difference in phase rotation is accounted for in the order of the phases, ABC versus CBA. Negative sequence is introduced on the system with untransposed lines, unbalanced loads, turn-to-turn and unbalanced faults, and wind and solar farm inverters programmed to supply negative sequence to faults. One consequence of having negative sequence on the system during normal operations is that it causes motors to experience counter-torque and skin effect heating. This could force the motors to need to be derated. Zero sequence consists of three phasors of equal magnitude and angle. Some sources of zero sequence are untransposed lines, capacitive coupling to ground, unbalanced load, and ground faults. Zero sequence is the only sequence component that doesn't return on the phase conductors by definition, and for this reason plays a role in all ground faults and grounding systems. Interestingly, odd triplet harmonics, third, ninth, 15th and so on also act like zero sequence. This can force the neutral conductor to need to be sized larger than the phase conductors. Here is a bit to help visualize how the sequence components relate back to the phase domain. Each component in the phase domain is equal to the sum of its sequence components for that phase. VA is equal to the sum of the A phases in the positive, negative, and zero sequences. The same is true for B and C phase. Remember that the alpha operator is a 120-degree rotation and its square is a 240-degree rotation. The decomposition of the phase space into the sequence space is just breaking it down into three parts that each have individual meanings by themselves. The diagram on the right is showing the result for a single line to ground fault. An identity of a single line to ground fault is that all three sequence components have the same current magnitude and angle. IA equals I1 plus I2 plus I0, or 3 times I0. The faulted phase is the red phase, and because all the sequence components for the red phases sum constructively together, the result is a large red vector. The sum result for the blue and yellow vectors is near zero. This is what you would expect for a single line to ground fault. All the fault current will be on one phase if I1 equals I2 equals I0. This will always be true for single line to ground faults at the fault. In a network, depending on how the positive, negative, and zero sequence current path to the fault, I1, I2, and I0 might not be equal elsewhere.
Thank you for watching. The next Coffee Talk will be about symmetrical components applied to faults. For an archive of Coffee Talks, visit www.nercspower.com. Email douglas.milner@nercspower.com to be notified for new Coffee Talks.